I'm Taylor Sullivan,
My name is Shaobo. Hello.
and we'll be presenting on the Knowledge Accelerator.
Mhm.
So the Knowledge Accelerator, Big Picture Thinking in Small Pieces, was written in 2016 and attempts to devise a method of crowdsourcing that scaffolds a large task and then distributes the components as small crowdsourcing tasks, with each crowdsourced individual unable to see the larger picture. The article addresses the problem of complex tasks necessitating a moderator to maintain coherency and fluidity. For instance, Wikipedia is heavily reliant on moderators to maintain the structure of an article for other members to contribute. However, when these key personnel leave the company, there are fewer individuals left to maintain the big picture, and it creates a bottleneck. This article mainly attempts to reduce the moderator requirement so that these big picture tasks can be entirely automated. So here's a chronology of the works we'll be discussing today. One of the works, CrowdForged, was written in 2011 and was a foundational work for this paper, as well as one of the inspirations for this technique. Then, of course, we have the Knowledge Accelerator itself, written in 2016. Similarly, we have Scaling Up Analogy with Crowdsourcing and Machine Learning. Came out around the same time as the Knowledge Accelerator, and it acts as a contrast to this paper due to its heavy reliance on machine learning over crowdsourcing. And then along the same timeline as well as SenseMap, also published in 2016 and offers further information on sense making as a concept to give context to the article. And then finally, we'll go over Flash organizations, crowdsourcing complex work by structuring crowds as organizations, which is a follow-on work to this paper, but with a slight mod. So to go over the Knowledge Accelerator, it's a prototype system that takes a complex question such as, how do I get my tomato plants to produce more tomatoes? And uses crowd workers to generate a coherent article that summarizes a variety of topics using multiple sources online to answer the given question without influence from a moderator. So the Knowledge Accelerator has a cost. The experiment awards $1 to anybody who completes the task, and takes about 5 to 10 minutes, with the total cost of answering a single question that's about $108.50, which you can see here, which is definitely less than the cost of a moderator. So the main task that these crowd workers are ultimately faced with is called sense making, which is the process by which we structure the unknown so as to be able to act on it. It's a quote from Carl Wick. This is an iterative process that involving the filtering of information and introducing structure to the information synthesis. The system these authors designed has a scaffolded architecture. And the key difference between this article and previous methodologies is that the Knowledge Accelerator does not require workers to decide on a structure before collecting the information from the crowd. This approach of learning from the data allows the answers to develop in a more dynamic way, similar to the way a human processes information. So in this approach, the authors implemented a crowd machine approach to sample a large amount of data in parallel and then cluster the information in topics. The main limitation of this approach is the motivation of the crowd workers themselves throughout the task, as well as the inability to filter through large volumes of information without a common thread. The crowd workers are consistently motivated to produce the easiest or most straightforward result, and has the potential to leave out large sections of more complex information that they just aren't motivated to read through. One of the main advantages of the author's approach is their description of future usage of the product for low frequency or highly personalized search queries. Topics that have sources that are highly structured and distributed, or for any information inside of a company's firewall.
Okay, so now let's take a look at the process and quality control implementation details about the Knowledge Accelerator. We could see that there are actually 6 stages of a complete process. for this system, which includes sourcing, clipping, clustering, integration, editing, and multimedia supplementations. Most of the stages consists of various subtasks that will be done by crowd workers. Expect that the clustering stage does the classification work by a combination of crowdsourcing and machine learning techniques. This approach takes advantage of the fact that many real-world tasks or datasets have long-tailed distributions, where a few categories make up the bulk of the head of the distribution, and many categories with few instances actually make up the tail. So specifically, there are two phases in this stage, in the clustering stage. So in phase one, the system applies support vector machine classification work, and then move to phase two, where the crowd workers by hand classify those clips that are on the low confident edges. Also, in terms of quality control, we have specific quality control techniques called open-ended set sampling and evaluate then act method, which either offers workers some training or generally offers some distribution of the whole data set before they truly start their works. And by doing so, the crowd workers could have some sense about the bigger picture without truly understanding it. And so the quality of their work is improved in a very efficient way. And now let's move to the experiment setup details. We could see that the author firstly defined 11 quite heterogeneous questions, and each of them will be processed by Knowledge Accelerator. Moreover, this question will also be simply Googled, and the return results of the top Google search will be used for comparison purpose. Of course, we had a separate set of crowd workers perform a pairwise comparison of the Knowledge Accelerator output to that of top results returned by Google. And here's a graph showing the result of this evaluation. One interesting note is that actually the higher the y-axis value of a result generated by the Knowledge Accelerator is, the worse it behaves compared with its correlated Google search. And so we can see here a majority of these results are actually beneath or under the x-axis. So we actually could say that this system beats its baseline and works well in most cases. However, this evaluation results also reflect some limitations for this system. So firstly, in terms of the question about how to use Vim editor, a number of the sources for this question actually were tutorials which actually have very specific ordering or steps. So in like the phase of clipping or in the clipping phase, these ordered tutorials were broken up into unordered clips, which creates an information model breakdown. And also, we have another type of question, which is about traveling to Barcelona. It seems like the Knowledge Accelerator's output did not outperform top web sources for these topics, especially like traveling, where there are heavy incentives for experts to generate well-structured content already in that source website. And in contrast, we actually could see that for the automation question, since a lot of experts separate their expert knowledge in different forums, Knowledge Accelerator works quite well for this type of questions. So for the future work, actually this system can be more focused on the support for the ordering tutorials web sources, and also how to outperform well-structured experts generated constants can be a really interesting question in terms of the future work. So let's now talk about more related works for this paper.
Okay, the first article we're going to discuss is the scaling up analogy with crowdsourcing and machine learning article. In scaling up analogy with crowdsourcing machine learning, the authors approach the problem of scaling up to find analogies in large, messy, real-world data. The authors in this article aim to respond to the issue of analogy mining with a crowdsourced approach, where workers identify analogies by querying a repository. Then these matches are used as a training data set for the deep learning algorithms. This is a similar concept to the Knowledge Accelerator's approach to find sources to answer a question. And this article was selected as a contrast to Knowledge Accelerator's methodology of using crowdsourcing almost exclusively to find analogous articles capable of answering a given question. This approach is an alternative and reduce the crowdsourcing requirements of the Knowledge Accelerator. This article addresses the issue of other analogy models relying on hand-created databases with high relational structure, which take hours to produce, or models that have trouble detecting in high-level concepts relational similarity due to a reliance on co-occurrence patterns. So here's what the interface actually looks like for the study. In A, you can query a product to find an analogous one. In B, you can search through the differing products. You can select the most analogous product in C. In D, you can explain what the analogy is or how the products are related. And then in E, you can highlight text that explains that analogy. So the author selected the Quirky dataset, which is an online crowdsourced product innovation website that has 10,000 product ideas that were unstructured and diverse across categories. The sample size was 400 products and 394 workers were utilized for the study, and each seed cost 10 minutes to complete, and workers could complete however many seeds they desired. So right here is the potential for bias if a skewed opinion decides to complete many seeds, which is a limitation of the study. But here is a query map of the varied queries that workers would enter for a given product. The corners represent queries that would result in the same analogy. So here you can see that cover and protect resulted in the same analogy. And this exposes the semantic similarities that past analogous models had trouble detecting. And then further away from the cluster, you can see related terms as well. This is the machine learning function that the authors came up with that learns the relationship between new pairs and whose score reflects the degree of analogy. So the authors used a Siamese network architecture, which you can see to the right, where words were embedded into a low-dimensional representation and combined into a matrix, then passed through several layers that extract word features, capture patterns, and filter noise. Then contrastive loss is calculated, which you can see the equation down at the bottom, where L positive penalizes positive pairs that are far apart, and L negative penalizes negative pairs that are closer than a particular margin. Learning is then done with gradient descent with back propagation. So the experiment, the data was split into training and evaluation data sets. The training data set had 12,500 pairs, and positive labels were determined by the worker, and negative labels were assigned by an implicit rejection of a product that appeared in a query. Evaluation was consisted of 3,000 pairs, and query results were incorporated into the model for the fact, and the accuracy was boosted from 0.46 to 0.54, as opposed to the previous version without the query results. When compared to latent semantic analysis, which is the traditional machine learning information retrieval similarity measure, the model had a much higher accuracy of 0.64 compared to 0.46, which you can see in the diagram. However, the downfall here is that the model throughout fails to address highly relational data. And to compare back to Knowledge Accelerator, the scaling analogy goal was a lot smaller. It's just to determine analogous text. The degree of distribution, you needed a strong training data set, but then you could develop deep learning algorithms that you could use with in the future. The workflow was entirely internal, and then there was more of a reliance on machine learning than crowdsourcing, but it did involve both, and the authors evaluate their model for errors throughout. Our next article is the sense map, supporting browser-based online sense making through analytic provenance. So this article takes on the problem of browser-based online sense making. This addresses the problem of users forgetting what they've already done in terms of gathering information to complete a task, and then having trouble retracing their steps in order to provide their sense making path to another person or review some information they previously discovered. So the model was designed on a collection of tasks that the authors wanted to satisfy during the collection, curation, and communication phases that occur throughout the information gathering process. SenseMap has 3 different views. The browser view, which is just your standard browser, but SenseMap collects data from that. And then there's the history map, which you can see to the left, and the knowledge map, which you can see to the right. And the goals throughout were to provide easy revisitation of past searches, location awareness of where an individual is in the sense-making process, and to show users the connection between different sources, and to present the process to a third party of the entire big picture of sense-making. So the browser view, again, it provides, it's just your standard browser, but it provides users with the function of highlighting and annotating browser data, and it collects the type, timing, context, and relationship of the particular source that a user navigates to. In the history map, a user can delete irrelevant nodes, minimize nodes that they're unsure about, and favorite extremely relevant nodes. In the history map, or in the knowledge map, on the other hand, you can add nodes from the history map, and the only difference is that all nodes are they need to be visible. And the main drawback here is that there's a lack of user commentary to define the structure in the knowledge map. To evaluate the model, 5 designers and engineers were introduced to the tool for 30 minutes and then given a task to complete, the task being the addition of accelerometers to measure movement intensity in ambulatory subjects. This map shows the path each of the participants took in the study. So P5 started building the knowledge map soonest and developed the most complex model involving 35 nodes and 35 links in the end. And then the first participant had trouble understanding the initial question and didn't start developing the knowledge map till the end. In a lot of ways, the article was similar to the scaling analogy article, but with a human-centered focus instead of machine-generated query mapping. 3 out of the 5 participants also who enjoyed using the model, which you can see participant 1, participant 2, and participant 5, were able to use it for its intended purpose. And then the other 2 acknowledged that the tool was semi-useful, but did not appreciate their experience with it. And then some participants, as you can see, lost trust with the tool altogether. But one of the main drawbacks is the study only involved 5 participants, so it's not very a diverse study. And then the conclusions drawn from this are that the users who were able to manage the addition of the browser history map and use the tool more often had a more positive experience with the tool, and they resulted in more cohesive findings. So participant 1, 2, and 5 had much greater coherence of schema. So the challenges that the authors faced were designing a more space manageable history map for users, and they decided to try to do that in the future. And then a summary that has occurred of what has occurred since the last actions on the history map So when a user navigates back to the history map, they can see what sources they've gathered since then, and then can add those into the history map. And then automatically summarizing and condensing the inactive portion of the map could resolve several issues as well. And then further research into the trust issues that developed as a user used the tool would also help. To compare this back to the knowledge accelerator, this was a much smaller task than the knowledge accelerator. Is just making a user-friendly visualization of sense making, and there was no distribution at all. And the workflow was user-centered, and very little machine learning was involved, and no crowdsourcing at all. And then there was some error checking where they evaluated their results, but overall, I think the sense map could potentially help the knowledge accelerator during the first phases where users are looking for sources and trying to make sense of the question itself. And that's why this article was selected.
Okay, so now let's take a look at a previous technique of the original paper, which is called CrowdForge. So CrowdForge is basically derived from a very classic paradigm, which is called map and reduce. So for those who doesn't get very familiarized with it, a map reduce can basically consist of like three basic tasks types. The first one is called partition, in which a larger task is broken down into like discrete subtasks. And also there's tasks called a map, in which a specific task is processed by one or more workers. And also we have like reduce tasks, in which the result of multiple workers' tasks are merged into a single output. So basically, CrowdForge abstracts away many of the programming details of creating and managing subtasks by treating those kind of steps as a basic building blocks for distributed process flows, which enables complex tasks to be broken up systematically and dynamically into sequential and parallelizable subtasks. And here are some features of this system. So some worth mentioning ones includes like it supports dynamic partitioning, so that like the workers themselves can decide a task partition, with their results in turn generating new subtasks. Also, like there's kind of a variety of quality control method, including voting, verification, or merging items. So to talk more details about like quality and control stuff, actually like this system supports examination the previous step by replicating map and reduce steps. So for example, if the user of the CrowdForge wants to guarantee the work of the partition, he or she can actually make some map tasks to generate and evaluate the partition jobs. And the crowd workers of those map tasks can all do the same partition job and vote for the best one. So actually, in reality, like as you can see, like a complete workflow of a CrowdForge tasks is not as easy as like the map reduce graph as I have shown before. There can be like multiple levels of the hierarchy that doing the partition job, and like multiple map and reduce in the different places or different levels of the hierarchy. So in terms of like the similarities and difference of the knowledge accelerator and CrowdForge, the goal of knowledge accelerator is mainly focused on like the knowledge aggregation, where the CrowdForge is mainly doing the writing jobs. And in terms of like the editing mechanism, we have mentioned before, like the knowledge accelerator has something called like vote then edit, which basically tries to relieve the danger or the threat from like independent workers generate the passages or the articles that has like no pattern similarities between each other, while like the CrowdForge actually can lose global coherence by independent workers. And for in terms of like the workflow, the CrowdForge have like a repeatedly generated hierarchy for like multiple partitioning jobs. And in terms of like the timing for decide like the structure of the output, Knowledge Accelerator actually did better in this section because it decides like the structure after the information is collected by the crowd workers. And both of them actually supports multi-stage quality control. And actually CrowdForge is more vulnerable to like the dependency between those tasks that is done that are done by different workers. And also there's another, actually it is a future work, which is about Flash organizations, which actually use the crowdsourcing in a very different but interesting way. So Flash organizations are crowds that are computationally structured like organizations. They enable automated hiring of expert crowd workers into role structures and continuously reconfiguration of those structures to direct the crowd's activities toward complex goals. So there are basically like two challenges about crowdsourcing as organizations. So the first problem is about like organizations typically assume a set specificity, which is the ability for organization members to develop effective collaboration patterns by working together over time. And clearly for like the crowd with workers rapidly assembled on demand from the platform do not offer a set specificity. So our system or like the Flash organization encodes the division of labor into a de-individualized role hierarchy, which is inspired by movie crews and disaster response teams, which enables workers to coordinate using their knowledge of the roles rather than like their knowledge of each other. And the second challenge is about organizational structures actually need to be continuously reconfigured so that the organization can adapt as the work progresses. So, for example, like the organization system is expected to support features like um, adding roles, changing roles, or adding teams in the intermediate step of the work, in the intermediate step of the work. And coordinating like many workers reconfiguration is actually very hard in parallel. So this system basically utilize a pattern that mimic um, Git-like version control that we will discuss more details in the later slides. So in terms of like the first challenge, the whole Flash organization system is actually running on a system called Foundry. And this Foundry GUI basically supports the authoring of the Flash organizations. So the Foundry timeline, which is shown on the top left, displays all roles and current tasks. And the task description, which is shown on the top right, displays tasks requirement and allows the leader to hire a worker to fill the role. So basically, Foundry transfers the necessity of set specificity to a role-based task assignment. And in terms of version control, Flash organizations ideally require an approach that allows workers to explore changes quickly in a sandbox and then ask people up in the hierarchy to quickly review and merge them. And this is kind of like a version or a quality control approach for the quality guarantee of the whole task. And as we can see here, the output of the experiment is actually some specific tasks of users generated by this system. As we can see here, like the goal of the system can actually be quite various, like ranging from Android application to like card game and to web application. So in terms of like the similarity and difference between the Knowledge Accelerator and Flash organization, the goal of the Flash organization is kind of open-ended. There is some limitation of this system towards some specific goals, but in theory, like this system, Flash organization is kind of open-ended. And in terms of like the degree of distribution, Flash organization does require someone sitting on the top of the hierarchy to do some managing stuff like authorizing the requests from someone at the bottom of the hierarchy. And for in terms of like the workflow, Flash organization does support version control, but like for Flash organization, it does not have any machine learning technique or AI technique involved within it. And both Knowledge Accelerator and Flash organization actually support a lot of training or error control mechanism to support or to guarantee their quality of the work. Okay, so that is basically our presentation, and thanks for listening.